Thermodynamics is the study of energy and its transformations. Thermochemistry is looking at the relationships between chemical reactions and energy changes. So this is important in all sorts of everyday processes, including industrial applications, energy production and storage, chemical reactions, including all the chemical reactions that happen in our body on a regular basis. So there are two definitions of energy that we are going to be using in this class. The first one is the capacity to do work, where W is work. Work is some sort of force exerted over a distance, so we use force, F for force, times D for distance. And then the second definition is the capacity to transfer heat. So this is where we have heat that can be released from one object into another. We can model this by saying delta T, where delta means a change and T is the temperature, is equal to negative delta T2. But that's actually really, really simplified because temperatures are related to heats, but that heat and temperature are actually very different things. So in order to write this a little more correctly, we would have delta, again, change in heat of subject 1 is equal to the change, but the opposite magnitude of heat in the second piece, whatever that is. We can also put energy into two types. The first one is kinetic energy. We've already talked about that in this class. This is energy by virtue of motion. And the magnitude of kinetic energy an object has is dependent on its mass and its velocity. So again, kinetic energy is equal to 1/2 mass times velocity squared. So in this case, the red car is going faster than the green car, so the red car has a higher kinetic energy than the green car. In this case, the truck and the little car have the same velocity, but the truck is larger, so it has a greater kinetic energy than the small car. The other type of energy that you have probably heard of already that we will be using is potential energy. And this is energy by virtue of position or composition of object. So commonly we think of this as like something that is on at a high distance and has potential energy because of gravity, because gravity can exert a force on it. So we can say the potential energy is equal to the mass times the gravitational pull times the height of that object. So this is a comparison of kinetic and potential energy that I really like. So if we have a cyclist that's at the top of a hill, but the cyclist is resting, water break or something like that, that cyclist has a lot of potential energy but no kinetic energy. When the cyclist is going down the hill, and they're actively moving down the hill, they have both kinetic energy and potential energy because they're still up. And then when that cyclist is down as low as they can get, but they're still moving, they have only kinetic energy. So chemical energy is what we're really interested in this class. And a kind of very simplistic version of chemical energy is the potential energy that is stored in the arrangement of atoms. So we've talked about why atoms form bonds, and that is because atoms, when they're in their bound state and we have a fulfilled octet, then they are at a lower energy state. And so what we're looking at is if we have a reaction that releases energy, that means these products are found in a lower energy state than the reactants were. Okay, so again, we're having some sort of chemical change in this reaction that the overall products have a lower energy state, therefore energy will be released in the reaction. SI units of energy are the joule. So we quantify the joule as the amount of energy that is transferred to or work done on an object when we have the force of 1 Newton that acts on an object through a distance of 1 meter. Okay. So here are how we look at the joules. Again, this is a derived unit. Joules are kilograms meters squared over seconds squared. You also have probably seen something called the calorie. So this is the amount of energy required to raise the temperature of 1 gram of water by 1 degree C. This is actually a really small value of energy. So when we are talking about calories, we're normally talking about kilocalories. And here's the confusing thing. A kilocalorie is 1 calorie with a capital C. Sorry. Apologize on behalf of all Americans. This is really weird. So 1 small c is 1 calorie, 1 big C is 1 kilocalorie. That's just how it goes. We're weird like that. Let's see. And then another common unit of energy that you'll probably see or have already seen is the kilowatt hour. These are commonly used by power companies to measure electrical energy. I wanted to mention here that the SI unit of energy that we're going to be using mostly in this class, the joule, is actually really small, is a really small value. So, for example, a 100-watt light bulb will use 3.6 times 10 to the 5 joules per hour. So usually in this class, we're actually going to be talking about kilojoules of energy, and you'll commonly see kilojoules more in practice. All right, let's talk about operating regions. So we're going to be talking about reactions, and we're going to be talking about heat transfer and work transfer, and we need to get our regions of operation down. Okay, so we define 2 regions, one the system and the other the surroundings. So system is the portion of the universe we are studying. So maybe this is a reaction. Maybe it is all the liquid in a calorimeter. Maybe it is the human body. Whatever it is that we're interested in, that is the system. Everything else is the surroundings. Okay, so everything else. Now, when we're trying to do these studies, we try and take our system, have a point system, and then put it in surroundings that are then insulated, so we can assume that we're measuring all input and output. But in reality, the surroundings is the rest of the universe. So just for example, if we're in the lab, our system might be the inside of a beaker, and the surroundings might be the lab. The system might actually be the reaction that's happening in the water, and the surroundings are the water. Okay. And then before we can dive into thermodynamics problems, let's just review the first law of thermodynamics, and that is the total energy of the universe is constant. So you've probably heard this before in high school in physics. So this is where we come back to energy is neither created or destroyed. So the energy that's lost by a system must equal the energy gained by the surroundings, or vice versa. We cannot make energy out of nothing. Cover of Popular Science, showing a great Norman Rockwell drawing of somebody trying to put together a perpetual energy machine and failing. This is one of my favorite little cartoons. So if there's no wind, we turn on the fan, which is completely and totally ridiculous because there's going to be some sort of energy loss in the conversion of electrical energy to run the fan, and then some sort of loss in the air going to make the turbines run, and then there'll be heat loss and some sort of loss in energy of turning that back into the electrical grid. So this is a very, very bad idea. So if you ever see somebody driving their Prius down the highway with a fan on top so that they can generate more energy, you could just wave at them and tell them to take a general chemistry class, because that's actually more air drag than they're making in energy with the fan. I mention that because I have actually seen that myself. Somebody driving a Prius down a highway with a fan on top.